time to settle. So, this week you guys have been covering trusses. And that's what your quiz is going to be about today. So, I figured we'd run through a truss problem real quick. And we'll see how this goes. So, this is a problem, I guess it's from your textbook. It's a problem that they ran through in SI a long time ago, too. And so, the question is asking, determine the force in members CD, CF, and CG, and state if these members are in tension or compression. So I'm going to go ahead and draw little stars by the members that we want. So CD would be right here from C to D. We've got CF, which is this little diagonal one here, and then CG, which is this vertical one here. So as we know, or as you hopefully know, there are two ways to go through in solving forces within each member of a truss. There's one way called method of joints, which is where you basically pick out one joint and draw the free body diagram of that joint with all the members acting off of it. There's also another method, members of sections, which is where you'll take a cut through a certain section of it and it'll kind of expose what the forces are in those beams, and you'll use that to solve for the beams. So, does anybody have a guess on which method we're going to use to find these forces? What's up?
The joint one.
The joint one? Yeah, you're not wrong. We are going to use the joint one for at least one of them. We're also going to use method of sections. So, it's a little bit of a trick question I asked you there. So, it's kind of hard to explain the differences, but essentially method of joints works really well if you're trying to find every single member within the beam, because then you could just go through and cycle through and draw all the free body diagrams. But method of sections is great when you only have a few that you're looking for, which if you look here on this truss here, you can use method of sections to cut through. Now you could very easily use method of joints and go through all of the joints here, but I'm going to show you guys method of sections on this. So the first thing that we're going to want to do is we're going to make this cut here, and once we make this cut, we are going to draw a free body diagram of one of the sides. I'm going to draw a free body diagram of this side here because it looks simpler than this side. So at our cut down this line here, we're going to have, I'm going to draw this kind of big. So this is D, E, and F. And acting on D going straight down is the 5 kilonewtons. Acting on E going straight down is 3 kilonewtons. And then you also have acting upward, or at least assuming upward, is the reaction force at E. And those are all the applied forces that we can see. Then we also need to take into account the forces within these bars here. So what you do there is you just, you always assume that they're in tension, and you just draw them pointing away like they are a force themselves. So you'll draw it like that, CD, and then you'll draw CF here, and then we've got GF down here, which is not one that we need to solve for, but it'll come in handy when we try to solve for CG later on. So these are our 3 unknown forces. Now, one of my biggest pieces of advice for these truss problems is don't use angles, if that makes sense. So if you're trying to find the direction, which way these are going in, don't try to do like the inverse cosine or tangent or anything to find the angle. I think the better way to do it is to use the triangles. If you guys have seen like 3, 4, 5 triangles and all that, a lot of times in these problems there'll be 3, 4, 5. If not, like this one, you'll just have to figure it out some other way. But let's see here. I'm looking at CF down there. If we look at CF here, and I'm going to draw off to the side here, just so we can see it. So CF, the dimensions of this are, for CF, down here it would be 5 meters. And then off to the side here it would be 3 meters. So if we were going to make our triangle to find the angles of that, would make it a 5, 3, And then this is going to be the square root of these squared, which is going to end up being the square root of 34, I believe. Yeah, the square root of 34 for that. And it's kind of ugly, but if you were to try to find the angles, I think that would be uglier and a little bit more complex, personally. If you are fine with the angles and can find them really fast, then go ahead and do that. But I think this is kind of an easier and nicer way to look at, and it'll come in handy. So on our triangle down here, we've got a 3, 5, square root of 34 on the angles there. And then if we look down below at GF, we've got, again, it's 5 meters in width or length, and then it goes up 2 meters. So it's going to go 5, 2, and then up here is going to be the square root of the sum of these squares. So that's going to be the square root of 29. Yeah. Can you guys see that okay, or is this a little bit messy? I can draw it bigger too if you'd like. But yeah, sometimes with these truss diagrams, if you don't draw them big enough, they get really kind of tight with all the stuff you're trying to find. So we've got our 3 forces here and the triangles. Another thing I'm going to draw is I'm going to draw point C, which we would have up here. Point C isn't really connected to anything in this, but it does give us kind of a measure of distances and whatnot, because the force CF is pointing to point C, and so is the force CD, and so they both kind of converge there. And then I'm also going to draw point G, just to round it out a little bit. And then we'll, of course, want dimensions. So this is 5 meters from C to D, or G to F, and then another 5 meters here. And then height-wise, we've got, let me fix that a little bit. Height-wise, we've got 3 meters from E to F, and then from F to G, it's down 2 meters. And so that should be the free body diagram of the section that we need to find all the forces within there. And so from here on out, we can treat it like it's a normal, I guess, equilibrium equations. We can treat it like it's a normal free body diagram now and find the forces using equilibrium equations. But these are a little tricky because we have the 3 unknowns here, and in the directions that they're pointing, they're kind of hard to solve for, because you can't just solve for them in the x, because you've got 3 going in the x direction, the CD, CF, and GF. And you can't solve for them in the y because you've got 2 unknowns going in the y with GF and CF. So we need to find a way to cancel out 2 of the forces so we can find the third one. Well, the way that we're going to do that is we're going to take the moment about point C here. Because when we take the moment about point C here, the line of action of CF is going to C. So that means that there is no distance, and therefore there would be no moment at C caused by CF. And then kind of the same deal with CD. CD is going to point C, and its line of action would intersect, if I drew like a little line here, so you could see it. They intersect there, so there would be no moment caused by these 2 forces. And therefore, the only force that would cause a moment would be GF right here, about point C. So we're going to go ahead and write out what that equation would be. So we've got the sum of the moments about point C is going to be equal to, so if we look at point C, we can go through and find all the forces that cause moments. I'm going to start going out and then back in. So first thing we've got is the 5 kilonewtons going down. With right-hand rule, it'd be curling downward, or going around it this way in a clockwise way. So that'd be negative 5 times, negative 5 times 5, because it's 5 meters away. And then next we've got the 3 kilonewtons here, so that'd be negative 3 times 10, because we got 5 and 5, it's 10 away. And then we've got EY. Now, we haven't found EY yet. It's still an unknown. And I kind of left it that way on purpose. One of the first things that you might want to do looking at these truss problems is to find the force reactions of all the supports. But in our case right now, we don't really need the support reactions at A, because they're not on this side of the free body diagram. So ultimately, all we need is the reaction at E, which we can find by taking the moment about point A for the entire truss here. So if I write this off to the side, I'm going to do kind of up top here, the sum of the moments about A, and of course we'll go through and do all of these, is going to be first -4 times 5, and then -4 times 10, and I'm just going to write it down below. So it'd be -5 times 15, and then -3 times 20. And lastly, we can assume that the pin would be going up. So I'm going to do a positive EY times 20. And all of those added together are going to be 0 because it's not moving. It's static right now. And so when we do that, we're going to find out that EY is equal to, I have it as 9.75 kilonewtons going upward. And so when we know that, we can write it in down here, 9.75 kilonewtons, and that's our EY. So does that make sense to everybody? Am I going too fast, or am I going like the right speed for you? Okay, getting mostly thumbs up. Cool. So we've got, if we go back to our moment about C here, we've got the 5 kilonewtons going clockwise, the 3 kilonewtons also going clockwise, and now we've got EY pointing upward, which makes it go counterclockwise and therefore positive. I'm just going to go ahead and write in 9.75 times 10, because it's 10 away. And then this is where it gets maybe a little tricky to visualize it with GF down here. With GF, to find the moment, we want the distance between the point and where it's acting. It's kind of hard because GF is at an angle. So what we're going to do here is we're going to split off GF into its X and Y components and find it there. So I'm going to start off with the X component. If we find the X component of GF, using this triangle here, it's going to be the horizontal, or it's going to be GF multiplied by the horizontal divided by the hypotenuse, if that makes sense. So if I draw a little note down here, got 5, 2, and square root of 29, and this is GF. If you guys kind of remember what sine and cosine mean, sine is like the opposite over the hypotenuse, and cosine would be the adjacent over the hypotenuse. Essentially, we're doing the same thing, but instead of saying sine or cosine of an angle, these themselves are our sine and cosine. So when we write GF here, we're going to write GF times 5 over the square root of 29. And that's going to give us what GF is along this horizontal here. And if you think about it, 5 is the adjacent, and square root of 29 is the hypotenuse. So therefore, that would be the same thing as cosine. So now that we know that, we have it going in the X direction. And the way that it's pointing, it would be pointing this way, which means it would be a negative moment. And then the distance from C would be, because we have it in the X, we're going to take the vertical distance, which is the 3 meters down. So times 3 meters. So we've got that, and I'm running out of room again. So I'm going to go ahead and write down here, right below it, continue on with the equation here. Now we want GF in the Y component. So we're going to take GF. This time we're going to multiply it by 2 over the square root of 29. And if we look at it here, it would be kind of pointing downward. And if it's pointing downward, we can see that it's, again, going clockwise. So pointing downward, and its distance from C if it's going down, is going to be this 5 meters here. And that's going to be negative. And those should be all the forces that are causing a moment about point C. So we know that we're going to have 0 right there. And from here on, it's just algebra, which there's not much of a point of showing you the calculations. I'm just going to go ahead and tell you what I got is GF is equal to 12.05 kilonewtons. And this we have in tension. And the reason why we have it in tension is essentially we assumed it was already in tension. When we drew the arrow pointing away from this joint here, or this point, we drew it pointing away, which essentially means that we assumed it to be positive, we assumed it to be pulling on it, we assumed it to be in tension. And when we calculate it out, we get the answer GF is a positive 12.05. And because we got that it was positive, that means that our assumption was correct and it is in tension. And so now that we know GF, we can go through and start solving for some others now. So the next thing we want to look at is we still have 2 unknowns here. And so we still can't quite solve for forces in the y. Well, I suppose we could solve for forces in the y to find what CF is, and then solve for forces in the x to find this. But what I like to do a little bit more is I like to take the moment about another point so we can find what CD is. So I'm going to take the moment about point F right here. So we're going to take the sum of the moments about point F. And the reason why is it clears off our GF because it's acting on that point, and it clears out our CF because it's acting on that point. And so the only unknown we're left with is CD right here, so we can solve for it. And this is kind of a guess or a checking type thing. I think you could technically do some of the forces in the X or some of the forces in the Y to find what CD and CF are at this point, but that also relies on you knowing GF. And so if we somehow got GF incorrectly, then doing that method, we would find the incorrect CD and CF. So by taking the moment here, we kind of eliminate those factors, and therefore we should get the right CD, even if we did get one of the other forces incorrect earlier. So I'm going to go ahead and do that. The moment's about point F. We are going to have, going positively, CD times, and it's going to be 3 meters up. And it's going to be positive going around counterclockwise. The 5 kilonewtons doesn't cause a moment because it's acting in line with it. And then we're going to have the 3 kilonewtons minus 3, and it's going 5 away, going clockwise. And then the EY would make it go counterclockwise, 9.75 times 5. And those should be the only forces causing a moment of F. So we're going to solve for that equal to 0. When we do this, we're going to get CD is equal to 11.25 kilonewtons. And it's going to end up being negative the way we do it. And so when it's negative, we're going to get CD is equal to 11.25 kilonewtons in compression. And that's one of our answers, so I'm going to go ahead and box that. Okay, does that make sense so far? Okay, cool. So now what we're going to do is we're going to sum for forces in the Y for the entire thing. So we have GF, and we have CD, we're just missing CF. So you could solve for in the Y or in the X. I decided to solve for in the Y, but it doesn't completely matter. If you're on an exam and you have some extra time, it might actually be within your benefit to solve for F in the Y and the X just so you can check your work, and you should get the same CF. But here, solving it for in the Y, we're going to have CF, and then again, looking at our triangle here as we drew, in the Y direction, it's going to be 3 divided by the square root of 34, and it's going kind of upward, so positive, and then we've got 5 going down, minus 5, 3 going down, minus 3, and then EY, which is the 9.75, going up. And then we've got I'm just going to go ahead and write it in GF, and GF would be kind of pointing downward. So it would be minus GF times, this would be the 2 over the square root of 29. And so we know what GF is. GF is equal to a positive 12.05. And so when we substitute that in and do all the algebra to find what CF is, we end up getting that CF is equal to 5.30 kilonewtons. And it ended up being positive, so we're going to write it in tension. So those are two of our forces that we needed to solve for. Now, lastly, I asked for CG, which we've got here on this vertical beam here. We can't really do method of sections for that, because if we tried to section it off, we'd end up cutting through a lot of different things. So what we're going to end up doing, or what I did, was method of joints about point G here, because it seemed like it was the least messiest, it had the least amount of forces on it. So I'm going to write kind of off to the side here, joint G. And so when we have joint G, I'm going to draw the free body diagram of what that is. What we've got acting in the vertical here is CG, our unknown, and it's just going to be going straight up. And then going up to the right here is going to be GF, which we found earlier to be 12.05 in tension. So I'm just going to go ahead and write it as 12.05 kilonewtons. And then on the other side, we've got GH. And that's also unknown, but it's not very hard to solve for. And we've still got our triangles here. It's going to be the same angle. It's going to be our 5, 2, square root of 29. And GH, because this is symmetrical, is going to end up being the same thing, but kind of in the opposite direction. Square root of 29. Now, by inspection, you might be able to tell what GH is just by looking at it. But I'm going to go ahead and write out what GH is. So to solve for it, we're going to take the sum of the forces in the x. And so we've got it in the x, it's going to be equal to 12.05 times 5 over the square root of 29 minus, I'm going to draw a little outcropping here, and then this is going to be GH times 5 over the square root of 29. This is going to be equal to 0. Well, this is really messy, and I apologize for that. But when you take a look at it, you can find that these both have the same 5 over the square root of 29. So that means we can cancel those out. And essentially we're going to have GH is equal to 12.05 in tension. And you could, if you're on an exam or something, you could say like by inspection, or I was able to see that these two would be equal just because they're the only forces in the horizontal. They should be equal because they're at the same angle. But if not, it's always a good idea to show the equation just to be safe. And so knowing these, we can now sum for the forces in the y. So summing for the forces in the y, we have CG, which is going upwards, so it's positive, plus we've got 12.05 times 2 over the square root of 29 on this side, and then we've actually got the same thing on the other side. So plus 12.05 times 2 over the square root of 29 equals 0. And when we do the math for this, we end up getting CG is equal to a negative 8.95, which that means CG is going to be 8.95 kilonewtons in compression. Okay, and that's the problem. We found our three forces that they asked us to, CD, CF, and CG, which we've got here, and this is all the work that we did to find them. And so we used method of sections first to find what these forces in the middle were here. And that it is kind of time consuming, but finding method of joints from E to D to F and G might also be kind of time consuming. It kind of depends on where you're feeling and how comfortable you are with each method. And so we use method of sections there to find these two forces, and then we use method of joints here to find CG, using the joint G here. So does anybody have any questions about that? No? Okay, that sounds good. So compute the magnitude of the forces in members GF, CE, DE, and DC. And I put stars by them. And list them as either tension or compression. So one thing I forgot to mention in our past problem, partially because it didn't come up, is probably the first thing you want to do is look and see, are there any zero force members? And so looking at this diagram here, do any of you guys see a zero force member? All right, which one is that?
CE.
CE, yes, I agree with you guys. CE right here is a zero force member, and that's because here at C, we've got a flat joint here, and this is the only one going here. I'm going to go ahead and draw like a free body diagram of what that joint looks like, just for explanation purposes. I think it helps to see. So joint C, at joint C, we've got CD, and let's say BC, and then we've got CE. Well, if we were to take the sum of the forces in the Y, it would just be CE, and nothing else is in the Y, and that equals 0. So therefore, we have to get CE is equal to 0. So hopefully that was simple enough. Next, we've got CE, so I'm going to go ahead and draw a circle here for zero force member, and we can write or box around CE is equal to 0. So that's pretty easy. We can check that off our list. Next, we could either go for GF, or we could go for CD. Personally, I wanted to go for CD. That looked more fun to me than GF. So for CD, we're going to use method of joints, and we're going to take the method, or the free body diagram of joint D down here to find what CE and CD is. And so we'll go ahead, write out joint D. We've got acting down on it, 10 kilonewtons. Acting to the left is going to be CD, and acting upward is going to be DE. And DE, again, using the triangles here, if we look here, it goes over 1 meter and up 2 meters. And so it's going to be 1, 2, and then this hypotenuse here is going to end up being square root of 5, because it's Pythagorean theorem there. And this is all we know about here at joint D, but that's really all we need to know. And so we've got two unknowns, and we've got two equations that we can use. The equation that we should start with is sum of the forces in the Y. And that's because we've only got one unknown in the Y here, because CD is completely horizontal. There is no Y component. So we've got DE. So we've got DE, and to make it go upward or just get the Y component, we would multiply it by 2 over square root of 5, and then minus 10, and that's equal to 0. Using that, we get that DE ends up being equal to, if I take a look here, 11.18 kilonewtons, and it ends up being positive, so we'll write it in tension. Okay. Next, we'll take the sum of the forces in the X. So sum of the forces in the X. And what we have here is we got CD acting to the left, so I'll draw as negative CD. And then I'm going to draw, or just write it in as DE still. I'm not going to replace it with the force yet. So write it as negative DE times, and to get this in the X, it'd be 1 over the square root of 5. And those are the only two forces going in the X. So we get that equal to 0. The reason I wrote DE in still as an unknown is it helps us visualize which direction the thing is going. It's a pretty easy substitution here because we've assumed it was positive and it ended up being positive, so it is going in this direction. But if for whatever reason it ended up being negative, or it was in compression and pushing inward, it might be kind of confusing if we were to just try to put it in right now. So I'm going to write it in this form here, and then we'll go ahead and substitute it in. So minus 11.18 equals to 0. And then doing this, we end up finding that CD is equal to, it's going to end up being a negative number here. So we're going to write 5 kilonewtons in compression. Okay. So we know what DE and CD are. We can check those off of our list up here. DE is good. DC is good. And now all we have left is GF. And so for GF, what we could do, or what we have to do, is essentially method of joints again. We could start from over here and just get it going all the way up here. I don't really want to do that. So the other method is to find joint G here and then find out what this reaction is. So in order to do that, I'm going to take the sum of the moments about point A. And this is for the overall structure. So the sum of the moments about point A is going to be equal to, I'm going to assume that GF, or the force here at G, is going to be acting to the right, just positive. So it's going to be negative GF times 2. And then we're going to have negative 12 times 1 for this force here. And then negative 10 times 4. And that all equals to 0. And that gives us GF is equal to negative 26, or 26 kilonewtons going to the left. And so now that we know what GF is, we can use that to solve, or we know what, I'm sorry, that's not GF, that's the reaction at G. Or maybe in this case, GX. So we've got GX up here, and now that we know what GX is, we can use joint G to solve for GF. So here at GF, if I got 26 kilonewtons going to the left, we can draw it as such, 26, and then going to the right, we've got GF. And so using this, we could solve for the forces in the X, and hopefully you should be able to see that it just means that GF is equal to 26 kilonewtons, and it's going to be in tension, because they're positive. And so we can check that off of our list, and we've got all the forces we wanted to find there. So this was an exam problem when I took the exam, so I'd assume you'd find something more like this. Hopefully nothing as complex as the problem you just worked on, but anything can happen, so I wouldn't be surprised if they do get more complex than this.